So we'll pick up with 12 here, which is about chemical bonding. So in chapter 12, we're going to talk about the different types of bonding that there are, ionic bonding, covalent bonding. We're going to talk about drawing Lewis structures. We'll also talk about molecular geometry involving the structures that we do draw. And we're going to talk about polarity as well. So let us get going here. So one of the ways that we do represent Lewis structures or drawing structures is through what is sometimes referred to as Lewis dot symbols, named after a guy named Lewis. Some people just generically call them electron dot symbols. So when atoms come in contact with each other, it is the outer electrons that do play a role. And as you'll see, hopefully in chapter 11 there, the outer electrons are those valence electrons. Those are the highest energy electrons there are. Those are the ones that are involved in bonding. So when two atoms come together, it is the electrons that really participate in bonding. So when we draw electrons, our Lewis dot symbols, we do only use the valence electrons. I know it auto-corrected all of it. There should be any. The valence electrons there in our symbol. A reminder that the quickest way to figure out the number of valence electrons is it is equal to the group number. So the number of valence electrons are equal to the group number. So everybody in group 1 has 1, everybody in group 2 has 2. Coming over here, group 3 has 3, 4, 5, 6, 7, and 8. So if you go with the group numbers, that will tell you really quickly how many valence electrons those elements have. You could also do it from the electron configuration and look at it. So if you looked at something like, say, 1s2, 2s2, 2p4, which is the electron configuration. Remember that when you look at electron configuration, these numbers here are the energy levels, basically. So 2 is obviously higher than 1. So all the electrons that are housed here would be the valence electrons. And for this guy, it would be both of those guys together in those orbitals. And that means that this guy would have 6 valence electrons. And if you look on the periodic table, that's actually the electron configuration for oxygen, which is hanging out right there in group 6. So you could either write the electron configuration, look at the highest electrons there are, and figure out how many valence electrons there are. But again, probably the easier way to do it is to just simply look at the group number on the periodic table. Any questions on that there? Okay. So a Lewis dot symbol will consist of basically the element symbol and 1 dot to represent each of the valence electrons. So basically we use the symbol. There's really no hard rule about how you place the dots. The only rule is basically there's no more than 2 per side. So a lot of times people will just kind of put a dot, 1 on each side, and then kind of go back and pair up. But again, really the only main rule there is not more than sort of 2 dots per side. With 2 dots per side, there's 4 sides. That's a total of how many electrons? That would be 8. Yes. And as we'll talk about in this chapter in terms of bonding, the ultimate goal of everybody when they make a bond is to end up with this number of 8. And that's because if we do look on the periodic table all the way there at the end, our number 8 guys are pretty much our noble gases. And our noble gases are very stable. They're chemically inert. So really the whole purpose of any type of bonding, ionic or covalent that we'll talk about, is pretty much for everybody to not change to those elements, but to end up with the same electron configuration as the noble gases. So they want to end up with the same number of electrons. It makes everything really, really stable. So here's an example of some Lewis dot symbols. Our electron dot symbols. I made when I was bored. I know, should get a hobby, but we'll see. So, but everybody here in group 1 has 1. We have 2, 3, 4, 5. One thing you should keep in mind, obviously, is here helium, which is a member of group 8, but it will only have 2 electrons because, frankly, helium only has 2 electrons, so it cannot have 8. So although everybody else there in group 8 will have 8 valence electrons, but helium pretty much will have 2, and that makes it really stable. That's why when we talk about it, hydrogen should only end up with 2 because that's all it needs to get over to helium's electron configuration. So everybody else in bonding wants to get to 8. Hydrogen should only have 2 because of that reason. It just needs to get over the helium basically to have the same electron configuration. Everybody past helium needs to get over all the way to the right-hand side there and end up with 8. So let's talk a little bit about ionic bonding first, but we can use Lewis dot symbols to help us understand really both types of bonding, both ionic bonding and covalent bonding. Ionic bonding is between a metal and a non-metal. And what happens in ionic bonding is the metal will basically transfer electrons to the non-metal. The result of it transferring the electrons to the non-metal is the metal will then become a cation that's positively charged. A non-metal will then become an anion that's negatively charged. And in an ionic compound, it is that attraction between the positive and negative guy that basically holds it together. There's absolutely no sharing of electrons in an ionic bond. It is solely the attraction between the positive cation and the negative anion that holds that together. And that's different than, as we'll talk about more in this chapter as well, covalent bonding. Covalent bonding is really 2 nonmetals. And the major difference here is they will actually share electrons. So what holds sort of nonmetals together is the ability to share electrons. They will not transfer them. The reason for that is those periodic trends, which again is in chapter 11 at the end there. That is why we do see this activity happen, because when we look at the periodic table, upper right-hand corner, we have things that have very high ionization energy. Ionization energy is the energy required to remove an electron, so it's very difficult to remove electrons. They also have very high electron affinity and electronegativity, which are 2 different things, but they both basically bring electrons to themselves with electronegativity, and they want to basically accept electrons with electron affinity. And that is basically our guys that will accept electrons. Opposite of that are kind of to the left of the periodic table. These are guys with low ionization energy. They have low electronegativity and low electron affinity, which altogether means they really don't care all that much about losing electrons. They don't want to bring electrons to themselves. It doesn't take a lot of energy for them to lose them. So these are typically where we find guys that want to lose electrons. And if you think about the periodic table, that's pretty much metals, which will lose electrons. And up on the right here, that is where our nonmetals reside, and that's where they will gain electrons. So what happens when we get a metal and a nonmetal together is, because of the very big differences in their periodic trends, the metal wants to lose their electrons and the nonmetal goes, perfect, I would like to take some electrons from you. They work really well together, and we get that transfer of electrons that happen. In a covalent compound, because they are both nonmetals, they are both basically hanging out up here on the periodic table, which means actually both elements want to actually gain electrons and take people's electrons. So what happens when 2 nonmetals get together, the best that they could do is go, we'll just share them. It's the best. I'm not going to give mine up. You're not going to give yours up. We're going to end up sharing the electrons between them. So that's the major difference between ionic bonding and covalent bonding. Any questions on that there? All right, so the general rule tells us, as we talked about, that elements in group 1 and 2 are likely to form cations. And again, as we go up or right on the periodic table into our non-metal region, those are guys who are going to form anions, especially when metals and non-metals get together. So let's take a look at ionic bonding, and this is going to be ionic bonding because lithium is a metal, fluoride is a non-metal, or that's fluorine. So this is definitely going to be ionic bonding. So when we look at lithium, and on the periodic table, lithium has an atomic number of 3, which means it has 3 protons. And if it is neutral, it would also have 3 electrons. And the electron configuration would be 1s2, 2s1, with this one right here being lithium's 1 valence electron. And also lithium's in group 1, so it has 1 valence electron, and that would be the 1. When it comes together with fluorine, which is actually group 7, it will have 7 valence electrons. And it would have a configuration of 1s2, 2s2, 2p5, and it would be these 5 electrons here, or I'm sorry, these 7 electrons, that would be its valence electrons from its electron configuration. So because of the differences here between the metal and the non-metal and their periodic trends, pretty much what's going to happen when these two guys get together is the lithium's going to go ahead and take my electron. And the fluorine is going to go, thank you very much. I'll take it because I do have some room for it. We'll put it in right there. The result of that is we will end up with the lithium losing an electron. And because it lost an electron, this is when lithium will now have a positive charge. So we'll end up with a positive 1 charge because it lost 1 electron. The fluorine will now become fluoride because it just picked up that electron. Right about there. And we'll have a negative 1 charge. And it is that positive and negative charge that is holding those guys together. There's absolutely no sharing of electrons here. So this is an ionic compound. A couple of things when we draw the Lewis sort of symbols to help us illustrate that. On the right-hand side there, we do need the charges to imply that they are ions at this point, and there is no sharing of electrons. And for the most part, usually people will put brackets around at least one of them, the negative guy. Sometimes people put brackets around both of them to indicate, again, that there's no sharing of electrons. There has been a transfer of electrons that occur. Any questions on that there? Now, if we look at the electron configuration in terms of what has happened with our lithium from the left-hand side when it had no charge to when it loses it, is it lost that electron, which means lithium will now have a 1s2 electron configuration in its +1 charge. And on the periodic table, number 2 is helium. So by lithium giving away its electron, what it was able to do is basically back up on the periodic table to the noble gas that came right before it. And now it has the same electron configuration as helium, which is a noble gas, makes it really stable. When we think about what happened with the fluorine, that 1 electron went right into that orbital. And that means that the fluoride here with a -1 charge will have electron configuration of 1s2, 2s2, 2p6. We add up all the top numbers. That's how many electrons there are. So that is 2, 4, and 6 is 10. On the periodic table, number 10 is neon, also a noble gas. So by losing and gaining electrons in this ionic bond, both elements were able to achieve noble gas configuration, which is pretty much the goal here of bonding. And that makes it a really stable bond. That makes everybody really, really stable. Any questions on that there? All right. So as I mentioned before, the Li plus, which is the cation, the F minus, which is fluoride, which is the anion, again held together by electrostatic attraction, which is the positive negative attraction between the two charges. And again, absolutely no sharing of electrons here. So if we look at another example, if we look at calcium, calcium is group number 2 on the periodic table, which means it actually has 2 valence electrons. Again, those are the outermost electrons, the one in the highest energy levels, the ones involved in bonding. If we lay up a little electron configuration, that's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4. And it would be the 4th energy level, which would be calcium's valence electrons, represented by the 2 dots there and the Lewis dot symbol. We are going to add it to oxygen, which I'll go over here. Oxygen is group number 6, which will have 2, 4, 5, and I'll just do it like that. 6 valence electrons. Once again, its electron configuration, 1s2, 2s2, 2p4 in this case. The 6 valence electrons, again, on the 2nd energy level in both of those orbitals, the s orbital and the p orbital. And again, if you add up the top numbers, 4 and 2 is 6, and those are the 6 valence electrons that we see in this picture. Once again, here we have a metal, which is calcium, which pretty much has all the properties of, I'm just going to let my electrons go. And we have oxygen, which is a non-metal, which has all the properties of, I would like to take your electrons, please. So that is essentially what's going to happen here, that exact conversation. And basically the result of that is calcium here will send over an electron. If calcium only sent over 1 electron, would that help calcium? It would not. If you just look on the periodic table, if it lost just 1 electron, it ends up at potassium, which is not a noble gas. So here it will lay up both electrons over to oxygen. The result of that is at this point, calcium has lost 2 electrons. And because it lost 2 electrons, it now will end up with a positive 2 charge as a result of the loss of those 2 electrons. And oxygen will now become oxide because it gained those 2 electrons. So that will allow oxygen here to gain those 2. It will also then gain a -2 charge as a result of that gaining of 2 electrons, has 2 extra electrons. Once again, it's the positive negative attraction between those 2 that's going to hold them together. And that again is an ionic bond. Once again here, because it is ionic. And I know that, by the way, without any need other than that is a metal and a non-metal, it's going to be an ionic bond. So you don't have to really think about it too much. As soon as you see metal and non-metal, always going to be an ionic bond. In terms of electron configuration, what's going to happen here is for calcium, it's going to lose those 2 electrons. So calcium with the +2 charge would be 1s2, 2s2, 2p6, 3s2, 3p6. And again, if we count up the top numbers, that's 2, 4, 10, 12, 18. And if we look at the periodic table, lucky number 18 there is argon's configuration, which once again is a noble gas. So by calcium losing those 2 electrons, if you look at the periodic table, is able to back up to the noble gas that comes right before it. The result of oxygen now is it will take those 2 electrons and it will throw it into that orbital where it has room for it. And when it gains a -2 charge, it will end up as 1s2, 2s2, 2p6, which again, if you count top numbers, 2, 4, and 10 electrons appear up on top. And that would mean that it has the same electron configuration as neon. So this is typically, as I mentioned, the goal of bonding, ionic bonding here. The way that both elements achieve noble gas configuration, or all elements achieve noble gas configuration, is the metals will lose electrons. The result of metals losing electrons is they will back up to the noble gas configuration that comes right before them. And again, in terms of the nonmetals, they will gain electrons. And the result of that is they will go forward on the periodic table to the noble gas that comes after them. So both, or everybody there, able to achieve noble gas configuration and be very stable at this point. Questions on that? Now, what happens if we take a couple that we did before? We take our calcium that we just saw there, which is 2 valence electrons, and really argon 4s2. Again, those being the 2 valence electrons. And we put it together with something else that we had before. We'll go with fluorine, which is group 7. So it'll look something like this, which again is 1s2, 2s2, 2p5. So when we put the calcium and the fluoride together, or fluorine together, metal, non-metal, so we know it's an ionic compound. We know there's going to be a transfer of electrons. So what's going to happen in this particular case is the calcium is going to send over an electron to the fluorine. At this point, can the fluorine take another electron? It cannot, because when it accepts that electron, it will now have 8. Yes, so you can't have more than 8, 2 on the side. But the problem, though, is, as we just talked about, if calcium only gives away 1 electron, it's only going to end up at potassium, which is not a noble gas. So in this particular case, because calcium needs to lose both electrons, but the fluorine here could only accept 1 of them, we actually need another fluorine hanging out there. So this second fluorine, which also has the same electron configuration, will now have room for our second electron on calcium to be lost. The result of this is calcium was able to lose both electrons and become positively 2 charged. Each of the fluorines actually only gained 1 electron, which means each of the fluorines, by gaining the 1 electron, will become negatively 1 charged, but there would be 2 of them in this case. I'll just draw it this way due to space. And it is that attraction between the +2 charge and the -1 charge in each of the fluorines that hold that together. In this case, if we look at it, all 3 of these guys have basically reached noble gas configuration. Once again, the calcium lost these 2 electrons, which allows the calcium to end up at argon's configuration. And each of the fluorines put an electron in that orbital. So 1 gained an electron there, 1 gained an electron there, which moves each of those fluorines to 10 electrons. So each of these guys also achieved neon's configuration. So all 3 of those things have basically reached the noble gas configuration. Yeah. You could, although in this case, since we're drawn out, a lot of times people will draw both of them out. You could do that, which would be okay. You also could, if you wanted to, like, sometimes people will draw the fluoride, one of the fluorides on the other side of the calcium with the calcium in the middle. So however you want to represent it. Yeah. Do you need to know them? You do not. Well, I don't know. I guess I should add it. Make sure we're talking about the same thing. So ask your question one more time. Sorry. So you do need to know that, as that's chapter 11 stuff. Yeah. So you do need to know that. To actually just draw these things, the knowledge to allow you to draw just the Lewis structures is how many valence electrons everybody has from the periodic table. That would allow you enough to do it. Here I'm including the electron configuration to demonstrate that everybody gets to that noble gas configuration. So if you were asked to draw this and weren't asked to include the electron configuration or anything like that, you could just draw the Lewis dot symbols by simply knowing how many valence electrons everybody has. You know? So yes and no, I guess, is the answer to that one. Other questions? Okay, so this also ties back to, I think last week we were talking about the very end of that chapter, when we do put ions together, right? We want to put the positive negative guy together to make sure that it does equal a overall charge of 0, if you remember. And so when we write the formula for calcium fluoride, The formula here would be calcium CaF2. And the reason that we do that is really for the reason above, by balancing out the charges in the simplest way to do so that it equals zero. What that basically means is everybody has achieved noble gas configuration. Everybody is stable. So if you remember at the end, I think it was chapter 4, maybe it was where we're at that point. Always positive, negative guys in ionic compound. When you write the formula, it needs to equal zero, and the simplest way to do so. And again, the basis of that is really the bonding aspect. It allows everybody to achieve that noble gas configuration. Any questions on that there? All right, so that is ionic bonding. Now we're going to talk about covalent bonding. So covalent bonding is a little bit different. Covalent bonding is always between basically two nonmetals. And again, because of those periodic trends, what we're going to end up with is actually sharing of electrons. So a sort of different type of bonding happening here, which again occurs with our nonmetals interacting with each other. As we will talk about here, the sharing may be equal sharing, or unequal sharing. And we're going to talk about how you can determine that a little bit later on in this chapter. But there is some aspect of sharing, like I said, either equal or unequal, but there is no transfer of electrons here. So if we look at two hydrogens, for example, that come together, hydrogen has one valence electron. Frankly, hydrogen has only one electron, so it can't have any more than that. So what happens here, because they're both hydrogen, and remember, hydrogen is a nonmetal, what's going to happen when they come together is they both will not let go of their electron. So they're both going to be able to share that electron between them, and they'll make a bond such as this that can be represented with two dots. Now, the two dots in the middle, which are the two electrons, go for the hydrogen on the left, and it also counts for the hydrogen on the right, which means in each of these cases, through sharing of electrons, each hydrogen basically has two electrons. And as we talked about a second ago on the periodic table, if you look up there, pretty much right after hydrogen comes helium, which is a noble gas. So hydrogen just needs to get to helium's electron configuration to be stable, and it should have two. Let me emphasize that hydrogen should only have two. People love to just, triple bond, double bond, triple bond, and put dots all around hydrogen. They go crazy with hydrogen when they start drawing pictures. If you're doing any of that, you should put a line through it because it's going to be wrong. So hydrogen pretty much should have only a maximum of two electrons, which means hydrogen will always be on the outside. It'll never be on the inside. And it will either look like, basically it will have, in most cases, if it's bound to something else, it will look like that with a line, which represents two electrons. Another way that we can represent this type of bonding is to use a line. And this line represents the two electrons that are being shared between it. It is a single bond. So one line represents a single bond in covalent bonding, and that represents basically one pair of electrons. We'll talk about it later, but a double bond is a two lines, which represents basically two pairs of electrons. And a triple bond is three lines in covalent bonding, which represents basically the sharing of three electron pairs. So in covalent bonding, because there's the sharing of electrons that occur, a lot of times people will draw sort of that bond between two things as a line. I personally will do that, but if you want to use dots to represent the bond between the two, you could do that as well. But most people will kind of use the line to represent the bond. Any questions on that there? So in a covalent bond, the electrons which are negatively charged are attracted to both nucleuses. So that's sort of what locks the electrons into place. The electrons are between the two atoms, and there's an attraction to kind of the electrons, the nucleus on the left, but also attracted to the nucleus on the right. So it kind of locks those electrons in between the two atoms, that sort of mutual attraction between them. And that is where we get really the bond that occurs between the two atoms, is those electrons that sort of get locked between the two with the attraction between the two nucleuses. So if we look at fluorine, for example, once again, if we look at fluorine's electron configuration, as we saw earlier, yeah. It is not. So electrostatic is basically the opposite attraction. And that's what happens in ionic compound. Covalent bonding it's basically, it is in a sense because there's an attraction to the nucleus, but it's not really sort of considered that. It's just that sort of sharing of electrons that occur. Yeah. So fluorine here, once again, 1s2, 2s2, 2p5. And if we had two fluorines, each of them are group 7, which means they both would start out with 7 valence electrons. And again, the 7 valence electrons would be those guys right there. And in this case, because they both have pretty much the identical periodic trends, they're both going to want to share those electrons. So fluorine is actually the most electronegative element you could have. Is the one that basically will want to bring electrons towards itself the most. The result of that is we will end up with the fluorine sharing electrons here, which can be represented in 2 ways. Either with all dots, where the fluorine on the left are using those electrons in the middle and ends up with 8 electrons. The fluorine on the right, by sharing those electrons, will also end up with 8 electrons. Or again, you could represent this with a line that looks something like this. So once again here, very similar to the idea of ionic bonding, here with covalent bonding and through sharing of the electrons, both of the fluorine atoms are basically able to get to 8 valence electrons, which puts them in the same electron configuration as the noble gases, and again makes for a very stable bond. Ultimately, like I said, that is essentially the goal of all bonding, is that to get to that noble gas configuration. Any questions on that there? Now, when we look at this picture, there are a few different types, or a couple of different types of electrons that we actually see. All of the electrons that are represented in this picture here by dots, they are not involved in bonding. So if we look at all these electrons out here, here, they are not involved in bonding. The way I know they're not involved in bonding is there's no other element drawn next to them. So they're not sharing electrons. Those are what are referred to as non-bonding electrons. And most people call them non-bonding electrons these days. Maybe old people like me will still call them lone pairs. So if you hear lone pairs or non-bonding electrons, they represent the same thing. They are the electrons that are not involved in any type of bond formation. Our non-bonding electrons are lone pairs. Now, obviously, the electrons that are in this picture is represented by the line, is involved in a bond. So these electrons here are involved in a bond, and they also have a very creative name. They are known as bonding electrons. So the electrons that are involved in the bond are known as bonding electrons. The ones that are not involved in bonds are known as non-bonding electrons. It is only the bonding electrons that are typically drawn with a line. So we don't typically draw lines for non-bonding electrons. We only use lines for bonding electrons. Non-bonding electrons are always represented with dots, unless you find an old school organic teacher, but most of them are represented with dots along the way. You should always, when you draw Lewis structures like this, you should always include both of those electrons, both the non-bonding electrons and the bonding electrons, in your picture when you draw them. We're going to talk about the sort of order later on in this chapter, how to go about that. So Lewis structures, again, help us understand really bonding through the sharing of electrons and covalent bonding. A good thing to remember is in all these sort of Lewis structures, it is only the valence electrons that are being shown. All these elements have other electrons, which are known as core electrons. The core electrons are the ones further to the nucleus and not involved in bonding. So for example, if you looked at lithium's electron configuration of 1s2, 2s1, this is the valence electron. And these lower energy level ones closer to the nucleus are what are referred to as core electrons, not involved in bonding. The reason they're not involved in bonding is frankly, they are closer to the nucleus and they're held a lot tighter because of the positive charge of the nucleus. So they do not participate in bonding. It would take an enormous amount of energy to try to rip one of those guys out to be used for bonding. And it just doesn't happen under normal conditions. So if we look at water, here's the Lewis structure for water. And again, in the case of water, what we have here is the sharing of electrons that allows really all three elements in water to reach noble gas configuration. The hydrogen here, again, by sharing with the oxygen on both sides, allows each of those guys to end up with only 2 electrons, which is what it should have. And again, reaching helium's configuration, which makes it stable. And now the oxygen, by sharing with those hydrogens, is able to get to 8 electrons, which allows the oxygen to get to the noble gas configuration and be stable as well. In most cases, when you draw hydrogen in a Lewis structure, once again, as I mentioned, should look like this only. Basically, 2 electrons represented by that line. Never do this. That is way too many. Never triple bond it and do that or anything like that. So again, people sometimes go crazy with hydrogen, always want to put more things on it than it should. So hydrogen, again, should pretty much in everything that you draw look like the top there, basically one line to the hydrogen. And again, should be on the outside in a Lewis structure. So we've touched upon this as we've been talking, but officially, the reason or the rule that everybody follows when we do bonding is what's known as the octet rule. And the octet rule basically says that everybody will continue to make bonds until they have 8 valence electrons around them. And again, in covalent bonding, that's going to be done by sharing those electrons, and everybody will be able to get to that 8. Again, the exception to that in the bonding is our hydrogen that we just talked about. Again, will only get to 2 electrons. That is sometimes referred to as the duet rule, because again, only needs to get itself over to helium to be sufficiently good. So we did talk a little bit about this earlier, but again, a single bond, the bonding electrons represented by one line represents 1 pair of electrons, which does represent 2 dots basically, which would be like these dots. A double bond like CO2 actually has 2 double bonds. So sometimes it does take, like in the case of CO2, some double bonds to get to 8. So by carbon double bonding on both sides, it's able to get to 8 electrons. And by making those double bonds, it allows each of the oxygens on the outside to also get to 8 electrons. So sometimes you could suffice and meet the octet rule by just making single bonds. Sometimes you do need to kind of go to double bonds to get yourself to meeting the octet rule. And a double bond would represent, as I mentioned, 2 pairs of electrons, are basically 4 electrons, as we see here. 1, 2, 3, and 4 individual electrons are 2 pairs. And sometimes a double bond is not enough to allow you to get to the octet rule or meet the octet rule. So sometimes you do need to actually go to a triple bond to satisfy the octet rule. So In the case of something like nitrogen, you do need to get to a triple bond to do so. A triple bond is represented by 3 lines, are again really 3 pairs of electrons or 6 electrons to do so. So the nitrogen here on the right, able to get to 8 electrons by making a triple bond. Same thing here on the left, that nitrogen able to make a triple bond and get there. And then something like this carbon by making a triple bond with another carbon and sharing some electrons there with a hydrogen, able to get to 8 electrons on both sides. And once again, importantly here, we do see our hydrogen only has 2 electrons on both sides, which also allows it to be perfectly happy. So we are going to talk about sort of the order as to how to draw Lewis structures later on in this chapter. I will just say you should be cautioned that sometimes people want to like double bond and triple bond like right out of the box when they draw things. And usually you want to kind of save, as we'll talk about, double bonding or triple bonding for a situation where the octet rule is not met. So you can kind of fix it by double bonding or triple bonding. So you typically don't want to kind of double bond or triple bond a lot of times, like right out of the box. So in covalent bonding, electrons are being shared, and electronegativity, which is the ability of an atom to bring electrons towards itself, as we talked about in chapter 11, is really the big sort of issue or determining factor as to how those electrons are going to be shared. Are they going to be shared equally or unequally? So again, on the periodic table, it increases as you go this way, with fluorine being the most electronegative, and it decreases as you go down on the periodic table. And once again, as we will see here, that's the ability to bring electrons towards itself. So really electronegativity, and a lot of times we use it for covalent bonding to help us determine, are they going to be shared equally or unequally? You can also, as we will talk about here, use electronegativity to help you determine ionic bonding, but frankly, you don't really need that at all for ionic bonding, because ionic bonding is always a metal and a non-metal, and that's pretty much all you need to remember. So when we look at something like hydrogen, when this hydrogen is sharing the electrons we would expect to be shared equally, because basically they're both hydrogen, which means the hydrogen on the left is going to pull just as strong as the hydrogen on the right, kind of like tug of war on a rope. You got basically the same person on both ends, and they're going to pull pretty much equally, and the electrons are going to be shared really equally between them. Same thing that we saw with the fluorine example. Those guys would be shared equally because they're both fluorine. Whenever we have equal sharing of electrons, this is what is known as a nonpolar covalent bond. Most people just straight up call it a nonpolar bond. It's implied that it's covalent because it's nonpolar and sharing, but nonpolar covalent bond, nonpolar bond is when we get equal sharing of electrons. Because we have equal sharing of electrons, you could kind of think of that bond as being like neutral. There is no side where it's more negative. There's no side where it's more positive. Everything's being shared nice and equally between them. You have basically equal electron distribution. Now, if we take out, say, one of each of those, and we put them together and put a hydrogen and a fluorine together, now in this case, we would not expect the electrons to be shared equally. And we know from our electronegativity that fluorine is the most electronegative, which means when they go to share electrons in this case, the fluorine is going to go, I think I would like the electrons a little bit more than you. So the fluorine is going to really hang on to a lot of the electrons, are going to hang out near the fluorine. if my red scribble is electrons, and not so much electrons are going to be over there on the hydrogen side. The result of that is unequal sharing of electrons. And if the electrons are going to be hanging out closer to the fluorine side of that bond, would the fluorine side be more positive or more negative? It would be more negative. So what happens in this case is because of this unequal sharing of electrons and the electrons hanging out near the fluorine creates a partially negative charge. That's a delta symbol, so delta negative. And because the hydrogens are sort of having their electrons kind of move away from them, on the hydrogen side of the bond, it becomes a little bit more positively charged. And it can be represented like that with the delta symbols and positive, negative. We also sometimes will draw an arrow to represent this. And the arrow will look something like this, where it will always point to the more negative side of the bond. And the back side that kind of makes like a plus sign is to the more positive side of the bond. So that is what is sometimes referred to as a dipole arrow. Bless you. So a dipole arrow is sometimes drawn to represent a polar bond. And once again, the point of it heading towards the more negative side, or the one that's more electronegative, really. And the back end of it to the one that's more positive. This unequal sharing of electrons is what is referred to as a polar covalent bond. Bless you. Or just a polar bond. So a polar bond is one where we have unequal sharing of electrons. And the result of that is we actually do get sort of a charge that occurs within that bond, where one side of the bond is more negative, the other side is more positive. Any questions on that there? That's pretty much what this says. There's my smear, stuff like that. So we could represent it again with that arrow to show the shift in electron density. So we could think of sort of a polar bond as being between really the two other bonds that we talked about. So the three types of bonds that we sort of talked about here is on one side, we have an ionic bond. And that is always between a metal and a non-metal. Like our lithium fluoride. And in this case, we get a transfer of electrons, creating a cation that's positively charged, an anion that is negatively charged, and again, no sharing of electrons. It is that positive, negative electrostatic attraction that holds that together. So that's sort of one end of the spectrum in terms of bonding. On the other end of the spectrum in terms of bonding is a nonpolar bond, or a nonpolar covalent bond. That is between two nonmetals, where we have equal sharing of electrons. So like our F2 example, our H2 as well. And here we definitely have sharing electrons and it is equal. And in the middle is a polar covalent bond, where we have unequal sharing of electrons, also between two nonmetals, such as this guy right about there. Now, when we have that unequal sharing electrons, as we talked about, it creates a partially positive charge on one side, partially negative charge on the other. Why are they only partially positive charges and negative charges on the polar bond? Why are they just partial positive and partial negatives? They are only partially positive negatives because they're still sharing electrons. So there's still some aspect of sharing that's happening there in a polar bond, even though it's unequal sharing. They haven't fully transferred like they do in an ionic bond where we get a full positive charge, a full negative charge, because they're still kind of hanging on. There's still some aspect of sharing, and that's why they're only partially positive and partially negative charges in a polar bond. So one end, perfect equal sharing of electrons, other end, no sharing of electrons, electrons being transferred from the metal to the non-metal, and in the middle, not equal sharing, not so unequal that they transfer, but some unequal sharing of electrons between the two. Any questions on any of those types of bonding there? So how do we really know sort of, are we going to get equal sharing of electrons, unequal sharing of electrons? Once again, as I mentioned, it is really the electronegativity values that electronegativity that we look at to help us decide that. Electronegativity is based on electron affinity, which is the energy change that occurs when somebody gains an electron, and that increases as you go up to the periodic table and to the right, decreases as you go down and to the left. And ionization energy, which again is the energy required to remove an electron from an atom in the gas phase, and that increases as you go up and to the right on the periodic table and decreases down to the left. So fluorine has high electron affinity and high ionization energy. So it has a high electronegativity. And again, it is the most electronegative element you could have. Sodium, which is far over to the left there on the periodic table, has low electron affinity, has a low ionization energy. Both of those, again, basically say you can take my electrons, and it also has low electronegativity, which means it's not looking to gain electrons at all. And that's why, again, sodium will typically lose electrons. So a guy by the name of Pauling actually came up with a scale to measure electronegativity. And Pauling's scale runs from 0 to 4. 4 is the most electronegative. 0, not so much. Again, the general trend in electronegativity, as we talked about, increases up to the right with our fluorine and decreases as we come down here. So we can actually use what's sometimes referred to as the change in electronegativity values. So that's like sometimes referred to as delta En. That's the change in electronegativity values to help us determine whether or not we will have a polar bond, a nonpolar bond, or really even an ionic bond. If you do the difference in electronegativity values, which is simply taking the two values for each element in the bond and subtracting them. So you just subtract the two values. And if you do that and you get anywhere from 0 to 0.4, it's considered a nonpolar bond, really a nonpolar covalent bond. If you're above 0.4, which is usually 0.5, to below 2, that is considered a polar covalent bond. And if you're typically above 2 and it's not perfect, it is typically an ionic bond. So you don't really need it for the ionic bond, as I mentioned. As long as it's a metal and non-metal, it's going to be an ionic bond. But those are the general sort of cutoffs, if you will, when you're using electronegativity values to do so. So anywhere from 0 to 0.4 is considered nonpolar, which means we would expect equal sharing of electrons. Anywhere from really 0.5 to below 2 will be polar, which means we would expect unequal sharing of electrons. And typically speaking, a difference of 2 or more, or in that ballpark, is typically going to lead to an ionic compound when you do that. So let's take a look at a electronegativity table here with the values. Maybe we'll just take it should be a different one, or no? No, maybe not. Maybe this is the one we'll go with. All right. So if we look at these ones here and we take a look at the ones that we were looking at, we have LIF, we had HF, and we had something like F and F, right? Or F2, I guess is the way to do it. All right, so if we use these values, which are the values that you see here, get a little bit bigger here. If we look for fluorine, the value here is 4, which is the most electronegative element. So basically, this guy would have a value of 4. This guy would have a value of 4. The change in electronegativity here would obviously be 4 minus 4, which is 0. And 0 falls between 0 and 0.4, which means we would expect this to be a nonpolar bond like we talked about. When you do the difference in electronegativity and you actually do get a difference of 0, sometimes people will call that a pure covalent bond. So a pure covalent bond is really you have perfect equal sharing of 0 difference in electronegativity value. Is sometimes referred that. It is still a nonpolar bond, but sometimes people will classify especially because there's a 0 difference between them. Now, if we look at H, which is there on the left, that's 2.1. And our F, which is 4. So H has a value of 2.1. F has a value of 4. We just take the larger number minus the smaller number here. So we get a positive number. And we will end up with 1.9. 1.9 difference, again, is between 0.5 basically and below 2. It's almost a 2, but not quite there. So this will tell us that it is a polar bond in this case. If we look at lithium, which is here on the left, it has a value of 1. And again, the fluorine 4. So this is 1 and this is 4. Our change in electronegativity would be 4 minus 1, which would be 3. That is above 2, and it would be ionic in this case. Question on that there. Okay, so why don't you try some here? A bit bigger. All right, so determine using the electronegativity values. Are these polar, nonpolar, ionic? Let's do KCl. Let's do the bond between NO. Let's do the bond between SO. Let's do carbon and sulfur. All right, so based on electronegativity values there, okay, let's take a look and see. So we'll start with the KCl. So K is 0.8 on the left there. Cl is 3. So when we do the change in electronegativity, going to be 3 minus 0.8. That should be a 2.2. That definitely is above 2, so we should expect it to be ionic. Once again here, you really wouldn't even need the values because when you see K is a metal and Cl is a non-metal, it's ionic. You don't even have to worry about it, so you could go with that. You don't really actually need the electronegativity values, but it could help. Okay, a note on that, for example, the 2 cutoff is not perfect. So if you took something, say, like lithium and something like bromine here, the difference there where it would be 1.8, which is less than 2. So that 2 cutoff is not perfect for all ionic compounds. So that's why it's good just to go with it's a metal, non-metal is going to be ionic. You don't have to really sort of worry about it. We go with nitrogen, which is 3. And oxygen there right next door at 3.5. So the difference in electronegativity would be 3.5 minus 3, giving us 0.5. 0.5 is pretty much where polar bonds start. So we would expect this to be a polar, as is between basically the 0.5 and below 2 range. Question on that one there. Coming to sulfur, which is right there at 2.5. Oxygen still at 3.5. So our change in electronegativity, obviously 3.5 minus 2.5, going to give us 1. And 1 obviously is between the 0.5 and 2. So that means that it should be polar. In the case of nitrogen and oxygen, if we were to draw the arrow, which way should the arrow be pointing between nitrogen and oxygen? The arrow should be pointing towards the more electronegative. So it would be pointing towards the oxygen. And the sulfur and oxygen bond, it should be pointing towards the oxygen, yeah, as that's more electronegative. Any questions on those two? Carbon and sulfur. Carbon is 2.5. Sulfur is 2.5. So difference in electronegativity here is 0 when you take 2.5 minus 2.5. Carbon and sulfur is a nonpolar bond. So this demonstrates a good understanding of, you definitely, if you have two of the same elements, it's going to be a nonpolar bond, but it is possible to have two different elements that will actually share the electrons equally. The reason for that is what is sometimes referred to as the diagonal rule. If we look at where carbon is versus sulfur, they are diagonal of each other. So although one is further up, the other one is further to the right, and they cancel out their differences basically. They end up basically being the same. Happens in a few places on the periodic table, like nitrogen and chlorine, also diagonal of each other, usually like up and over or down and over one. You'll get that diagonal relationship between them. So you'll see some diagonal relationships. That's the only ones that maybe you need to worry about that might not be polar. Yeah. No, you would be provided that table if you need it. Yeah. You do need to know the general trend in electronegativity. Again, up to the right is more electronegative, down and to the left is least electronegative. But if you need a chart like that, you would be provided that for sure. Yeah. Now, do you actually need the numbers? And in some of the situations here, the answer is you actually don't even need the numbers. If you know the actual general trend in electronegativity, like we talked about, that it increases up and to the right and decreases as you go down and to the left. For example, if you look at the one where we had nitrogen and oxygen, which is right here, nitrogen and oxygen are in the same period on the periodic table, and oxygen is further to the right, which means you would expect oxygen to be more electronegative than nitrogen, and you can make a pretty safe, educated guess that it's going to be a polar bond because they're in the same period on the periodic table, and one's further to the right, it's going to be a polar bond. And if you look at the sulfur sort of oxygen one that we did, same deal, they're in the same group on the periodic table. And in this case, oxygen is further up in the group, which means it should be more electronegative. So you really wouldn't even need the numbers to make a pretty educated guess that that's going to be polar. So in general, you can make a pretty educated guess without the numbers, just using the general trend on the periodic table. Definitely something's in the same row or period, or something's in the same group, and one is further up or down, or one's further to the right. One's going to be more electronegative than the other and going to lead to a polar bond. So you could really, in general, be pretty right in most cases by just using the general trend. Questions on electronegativity? All right, we will lay it up there.